Number one, student A conducts an experiment to determine the speed of sound in air using tubes of different lengths. Each tube is open at one end and closed at the other end. A short pulse of sound is produced by a loudspeaker near the open end of each tube. A microphone is placed at the open end of each tube and detects the sound entering and leaving the tube. So this is the diagram of the experiment. The graph shows the variations with tube length L of the time t for the sound to travel along the tube and be reflected back. This is the diagram, the graph, with scatter plot. And look the distance 10 centimeters, 10 centimeters, 10 centimeters, 10 centimeters, 10 centimeters, right? The percentage uncertainty in its time measurement is 9%. The uncertainty in L is negligible. Question A. For L equal 40 centimeters, calculate the absolute uncertainty in T. Right. I would like to using symbol delta T for the absolute uncertainty. Delta T equal 9%. 9% is the percentage uncertainty in T over 100 multiply. We are going to find the measurement value when L equal 40. So we need to find T when L equal 40, when T equal 40 is 1, 2.2. 2.2 millisecond. So the result is 0.198 milliseconds. And after that, rounded becomes 0.2 millisecond. For L equal 40 centimeters, draw the error bar on the graph for this data point only. So we are going to determine the upper limit and lower limit. The upper limit equal T when L equal 40 minus delta plus delta T. It is 2.2 plus 0.2 according to this result. Equal 2.4. And then the lower limit, it is 2. T for T minus delta T, it is 2.0. So the error bar strike line from 2.0 to 2.4, this, the error bar. Draw the line of best fit. If we create a strike line of this, represent of this scatter plot, so we can sketch a strike line from the initial point to the final point, from this point to the final point. But I would like to draw the best fit bar. Of this, there are two at the upper straight line and this one, the lower. Okay. Of the main strike line. Determine using the graph the speed of sound, state, and appropriate unit for your answer. I will be using this bullet point, 30 and 1.9, while this one is 70 and 4.2, right? to coordinate point 30 and 1.9, and then 70 and 4.2. Right. So gradient of the strike line is T over L, because T is the vertical strike line and L is the horizontally strike line. So it is T2 minus T1. This is L2 minus L1. T2 is this one, 4.2 minus 1.9 over 70 minus 30. And if you calculate, the result is 0.0575. Okay, millisecond over centimeters. Because L unit is centimeters and T unit is millisecond. Now, speed. How about the speed? Speed or velocity is 2L over T, or it is 2 over T over L. That one. So 2 over this number, 0.0575, becomes centimeters over millisecond. And if you calculate this 2 over 0.0575, the result is 34.78 centimeters over millisecond. We are going to convert centimeter over millisecond into meter per second. So one meters is 100 centimeters, and millisecond is 1 over 1,000 seconds. So it's going to be, let's see, 4.78, 10 power minus 2 meters, and this one is 10 power minus 3 seconds. It becomes 34.78, 1 over 10 power minus 1 meter per second. It becomes 347.8 meter per second. Next. Student B conducts the same experiment. There is another student B. Student B conducts the same experiment and analyzes, but places the microphone 10 centimeters to the left of the open end of its tube. Right, so student B create the same experiment, but the positions of microphone is 10 centimeters to the left. Compare with reference to the graph drawn the value for speed of sound obtained by student B to that of student A, the value of speed, right? I have provided my explanation about it. If we compare experiment of student A and student B, student A, student A, the microphone is placed at the open end of the tube. In this case, the sound pulse travels the entire length of the tube. While student B, the microphone is placed 10 centimeters to the left of the open end, meaning the sound pulse travels at distance L minus 10 centimeters, which 0.1 meters shorter than the total tube length. Since the sound is reflected from the closed end, the total distance the sound travels in the tube will be twice the distance from the open end to the microphone. So it becomes 2 times L minus 10 centimeters. So how about their gradient? Student A experiment. Student A experiment has velocity or better is time equation. The time equation is L over V. Based on this equation, we can determine gradient of A experiment is 1 over V. So what students B? Students B has time equation is L minus 10 over V. And its gradient is 1 over V also. So you may compare that gradient A and gradient B same. 1 over V, 1 over V. Okay, same one another. How about their speed? Their speed, we can determine their speed through the formula that velocity of A experiment is L over T. Okay, T A, right? And velocity B is 2L minus 10, okay, over TB. It occurs on TB. And regarding the graph, if we compare the graph, so graph created by student B will be lower than strike line of student A. Okay, but they have same gradient. An experiment is conducted to measure the specific heat capacity of water. A mass of water is placed in a glass beaker and energy is transferred from an electric heater. So this is the electric heater and this beaker with water inside. Next, the data collected are mass of water, change in temperature of the water, energy transfer from the electric heater. This calculate the specific heat capacity of water. Right. So the formula is this one: C equal specific heat capacity equal Q over M times delta T. That's all. Q equal this one 16,000 over 16,000 joule over 0.250. This one mass of water multiply 14.0 in Celsius. So it's gonna be 4,571 joule over kg degree Celsius. Okay, if you change Celsius into Kelvin, it's no problem because the thermometer Celsius equal it change scale. If you change the scale becomes Kelvin, it's no problem because they have same scale, 100 the scale. If Celsius from 0 to 100, Kelvin from 243 to 343. Determine the absolute uncertainty in the specific heat capacity of water. Right. We need to determine first the relative uncertainty, relative, relative uncertainty in M in mass is equal 0.002 over 0.250. The result is 0.008. And then relative uncertainty in delta t. Okay. I'm going to check delta t is this one 0.5. Just now mass 0.002 now. Delta t 0.5 over 0.5 over 14.0. The result is 0.0357. And after that, relative uncertainty in Q. In Q, so let me check. 300 over 16,000. 300 over 16,000. And the result is 0.01875. So total relative uncertainty equal accumulation of this result 0.008 plus 0.0357, 0.01875 equal so total relative uncertainty, sorry, in C, okay, 0.06245. 1, okay, Joule over kg Kelvin. And now absolute uncertainty, the absolute uncertainty, wait, this one, absolute uncertainty, 0.06245 times 4,571.4. Actually, wait, let me see. This one, the first result. Okay, this is 0.43. Supposed to be 0.43, this one. 0.43. 0.43, and it's equal 285.46, rounded to 286 joule over kg Kelvin. Write down the specific heat capacity of water and its absolute uncertainty to the appropriate number of significant figures, right? So specific heat capacity, the specific heat capacity is C equal 4,571.43 rounded to 4,600 joule over kg Kelvin, while the absolute uncertainty in C, this one, I'm going, that is delta C. So delta C, 286 rounded to 300 joule over kg Kelvin. So the specific capacity of water, the specific heat capacity of water C, specific heat capacity of water and its absolute uncertainty is This number 4,600 plus minus 300 joule over kg Kelvin. Outline one source systematic error in the experiment and its effect on the calculated value of the specific heat capacity of water. I have provided my explanation, this one, that not all the energy provided by the electric heater is used to increase the temperature of the water. Some of this energy is instead transferred to the environment, to the air, environment around the heater, resulting in a lower temperature change in the water than expected for the given amount the energy input. Right. So if you pay attention, the formula C equal Q over M delta T. Okay. This formula assumes that the energy Q is used to heat the water, but energy loss energy loss in surrounding or in the environment because the calculations value of C, the calculation value of C becomes higher. So C becomes higher than the true specific heat capacity. It occurs uh, because the actual energy absorbed by the actual energy absorbed by water less than energy measuring from the heater. Yeah, that's the reason. Three, the length of a space station is measured to be 100 meters according to observer A at rest in the space station. Observer B is moving at 0.60 C. C is the light speed in vacuum with respect to the space station. Write down the length of the space stations according to Galilean relativity. According to Galilean relativity, that lengths are not affected by relative motions of observer. It means no matter how fast observer B is moving with respect to the space station, the length of the space station remains the same as measured by observer A. So the length of the space stations observed by observer B, it will still 100 meters. Okay, still 100 meters, according to Galilean relativity. Define what is meant by proper length. I have provided my opinion about it, about my answer about this question. This one, the length of an object measured in the rest frame of the object when it is at rest relative to observe, or the length of the object as measured by an observer who is stationary with respect to the object. Calculate the length of the space stations according to observer B with reference to special relativity. Special relativity, right? I would like to start with this one. This is gamma equal 1 over 1 minus square root 1 minus 0.6 square. Okay. Sorry, this is square. And if you calculate, it will be 1 over 1 over 0.8, and it is 10 over 8, 5 over 4, 1.25. Now we're going to find length of the space station. The formula is L equal L0 over gamma. This is L0 is proper length of the space station. The proper length is 100 meters over gamma is 1.25. And if you calculate, it becomes 80 meters, right? So the length of the space stations according to observer B with reference to special relativity is this one, 80 meters. So there is difference. Outline how the result in B part 2 contradict Newton's postulates concerning time and space. Yeah, because in Newton postulates, I have uh, provide my answer here. In Newton postulates, time and space are considered absolute. This means space is fixed and same for all observers. There are two reasons that this means space is fixed and the same for all observers, regardless of their motion. This is the first one. And the second one, uh, this is the first one. So time is the same for, according to Newton's, that time is the same for all observers, regardless of their state of motion. So now this is the first one. Okay, time and space are considered absolute. Time and space are absolute according to Newton postulates. Right. However, according to the special relativity, that according to uh, the second opinion of about the special relativity, that when observer B moves at 0.60 c relative to the space station, the length of the stations will appear contracted 80 meters. So space and time are relative. So according to Newton, that space and time are considered absolute, but according to special relativity, that space and time are relative. They depend on the relative motions of observers. The length contractions of the space stations from 100 meters to 80 meters occurs because the length of an object in motion changes depending on the observer's relative velocity to the object. So that's the difference opinion according to Newton postulates and special relativity, right? According to Newton postulate, that time and the main difference is or the difference opinion about time and space. According to Newton, that time and space absolute, while according to special relativity theory based on Einstein theory, that uh, time and space are relative. Number 4. The diagram below shows two particles traveling in opposite directions above the ground. The velocity with respect to the ground of particle A is 0.6 c, And the velocity of particle B with respect to the ground is minus 0.75 c. C is the light speed, right? Calculate the velocity of particle B according to particle A. Particle B, velocity of particle B according to particle A. It means velocity B to A, right? To find the velocity of particle B according to particle A, we need to use the formula for relativistic velocity addition. And the formula is like this: velocity B to A is equal velocity B minus velocity A over 1 minus VA VB over C squared, right? VB is 1 minus 0.75 C minus VA is 1, 0.6 C over 1 minus 0.75 C times 0.6 C over C squared. It becomes minus 1.35 C over 1 minus 0.75 times 0.6 is 0. It becomes plus here because minus and minus 0.45 C squared over C squared. So it's going to be minus 1.35 C over 1.45. And the result is minus 0.93 C. That one. The particles were emitted at the same time according to observer X at rest with respect to the ground. Another observer Y is moving parallel to the ground. Show that the particles are not emitted simultaneously in the frame of observer Y according to the Lorentz transformations equation. Okay, so we are going to using the Lorentz transformation, and the formula is this one, where I would like to write in here that Txn equal gamma times T minus Vx over C squared. Txn is time in the frame of observer Y. This is Txn, while this one T is time in the frame of observer X. So this Y, this is X. Then X position in the frame of observer X. V, this one V, is relative velocity of Y with respect to X. And what else? Oh, gamma. Gamma is Lorentz factor. Lorentz factor is this one. Gamma equal 1 over square root 1 minus V squared over C squared. That one. While C is speed of light, right? So for observer Y, the time of emissions is calculated according to the formula or according to the rule like this, T AXN. Okay. This is for observer Y. Gamma times T minus Vx A over C squared. And T Vxn gamma times T minus Vx xb C squared. Now subtract TAXN and TBXN. If we subtract, sorry, I'm going to subtract right like this. It's going to be TAXN minus TBXN, and this is delta T actually. Delta TXN, because TXN, and it is gamma times becomes minus this one 0, t minus t equals 0 minus becomes it is minus minus Vx minus Vx a, okay, over c squared plus Vxp over c squared, like that. So it's gonna be delta t xn would be gamma times minus Vx a, okay, and this is becomes minus Vx b, right, c squared. This is delta t. It's gonna be delta phi, delta phi, uh, phi delta x, I mean, and then it becomes p times xa minus xb, okay, c squared, and have it here, gamma times minus phi delta x over c squared, this, that one. So I'm going to add several information that uh, if if xa if xa if xa not equal with xb, then TAXN not equal or unequal TVXN. It means, or meaning, the particles uh, the particles are not emitted. I forgot to add this information. Supposed to be I have to type first. So the particles are not emitted simultaneously in the frame of in the frame of y. Okay, in the frame of y. Right. And the second I would like to writing here that the difference time, or the time, oh yeah, the difference time depends on the spatial separation of x b minus x a. So the relative velocity, and the Lorentz factor. So the difference time depends on the spatial separations xb minus xa, depends on the relative velocity, and depends on the Lorentz factor. This one, the Lorentz factor is gamma, right? What else? Yeah, I think that's enough. Number 5, the space-time diagram gives the city x-axis for observer A, the world line and x and axis for observer B are also shown. When observer A and observer B were at the origin of the space-time diagram, their clocks were synchronized. This diagram calculate the speed of observer B with respect to observer A. Right. The first step we need to determine gradient or slope of city action. Slope of city action is equal delta city action over delta x action, right? And it is the action is 1, okay, and this is city action 4 and 5. So delta city action is 5 and this is 4. So that one is 5, 4. And after that, the gradient or slope of x, then it is a delta ct over delta x. This one, okay, 4 over 5. Right. Velocity of velocity of observer B with respect to observer A, we can found using inverse of this gradient, and then comes velocity. Inverse it means c times delta x over delta ct, and that is c times 4 over 5 or 4/5 c. This for observer A, an event has spacetime coordinates x equal 3 and ct equal 1. Plot the point corresponding to the event on the diagram, label the point E, right? 3, wait, okay, this one, 3. This is the coordinate point E. Okay, and what else? According to observer B, if an E occurs before observer A and observer B meet, justify this statement using the space-time diagram. Right, so we need to find CT xn is gamma times x minus phi t. Right, for gamma, I would like to calculate gamma formula like this 1 over square root 1 minus 0.8 c squared over c squared. And it is 1 over square root divide this 1 minus 0.64 1 over square root 0.36 1 over 0.6 and that is 1.66. This one, that is gamma. So we can substitute it into this equation, becomes 1.66 times x equal 3 because plus 1 minus this one minus uh sorry, not 50 but phi x, sorry, wrong, supposed to be, this is ct, okay, so ct minus phi x over c, so it's supposed to be 1 because this is 1, ct equal 1 1 minus 0. Phi x is 0.8 c times 3 over c. Right? And this is 1.66 or 1.66 times 1.2.1 minus 2.4. And the result is minus 2.3. Okay. This formula according to Lorentz transformation. So next we're gonna find on uh on a strike line CT extent, we're gonna find minus 2.3. Minus 2.3, this minus 2, 1, 2, 3, this one. And we're gonna create the strike line from E, from E coordinate point E to here. Okay, the strike line, and you may create the strike line using your ruler. Determine the space-time coordinates of the event according to observer B. Right, according to observer B, it means x xn equal gamma x minus Vt. Just now I wrote this formula. It's according to Lorentz transformation, so it becomes 1.66 times 3 because x equal 3 minus 0.8 multiplied by 1. And if you calculate, the result is 3.7. 3.7 on x strike line. 3.7 on this x-axis strike line is 3.312 3, 4, 5, 6, 7. This one, 7, 8, 9. Yeah, this one, 7. Okay. I'm going to using a different color. You may using your ruler to sketch this, right? So we can state that the space-time coordinates, okay, space-time coordinates, the space-time coordinates 3.7, this number, comma, minus 2.3. This is the space-time coordinates. Show that the space-time interval between the clock synchronization and the event is invariant, right? So space-time interval we can determine through this formula S squared equal ct squared minus x squared. And this ct is 1 squared minus 3 squared equal 1 minus 9. And it is minus 8. Minus s squared equal minus 8. Invariant. Number 6. A solid disk initially at rest rolls without slipping down an inclined plane. The disk has a radius 5.5 centimeters. This is the radius from the center of the disk. The length of the inclined plane is 1.5 meters. 1.5 meters L. The time taken for the disk to roll down the inclined plane is t equals 0.96 seconds. State for this disk the relationship between linear displacement L and angular displacement theta. Right. The relationship when you look this diagram that this disk will uh, roll down from this position, from the initial position to the final position here, as long as L, it needs time, T equals 0.96 seconds. Okay, so it needs time. So it has R as the radius. So the relationship between the linear displacement and angular displacement theta and also involve R is this one, that L or length equal R the radius. It will roll down, okay, uh, with the angular displacement theta. So L equal the radius multiplied by theta. This if L or the linear displacement is the subject. So if if theta or the angular displacement the subject is the subject, this equation we can rearrange becomes L over R. So angular displacement equal the linear displacement over the radius. Calculate the angular accelerations of the disk. To determine the angular accelerations, I'm going to use the rotational kinematic equation that alpha equal to theta over t squared, which are alpha is the angular acceleration, t for time, and theta is the angular displacement. So we need to find theta first, according to this information that theta equal L over R. L is 1.5 meters, while R equal, I have to check first, R is 5.5 centimeters. So we have to convert centimeters to meters. 5.5 centimeters, 1.5 meters over conversion 0. Divided by 100, 0.055 meters. And if we calculate this division, it equal 27.27. The unit is radian, unit of the angular displacement. Next, substitute this value, this result into this formula. Alpha equal to times 27.27 over t is 0.96. Yeah, 0.96 according to the information squared. And if we calculate, the result is 59.186, rounded to 59. The unit is radian per second squared. The disk and a ring with the same mass and radius are released from the top of the slope at the same time. Explain without numerical calculation which one will reach the bottom of the inclined plane first, right? So I have provided my answer, my opinion about this question. One, the moment of inertia determines how easily an object can rotate. For a solid disk, the moment of inertia is, according to the information, the moment of inertia is equal half m r squared. Okay. While for a ring, the moment inertia is m r squared. The ring has a larger moment of inertia because all its mass is concentrated at the outer edge, whereas the mass of the disk is more evenly distributed. So if you compare this formula, that the ring has a larger moment of inertia, right? Because because of both the disk and the ring are rolling without slipping, they convert potential energy into both translational and rotational kinetic energy. The disk with a lower moment of inertia converts more potential energy into translational kinetic energy, which affects its speed, affected to the speed of uh, uh, the speed of the disk, and less into rotational kinetic energy compared to the ring. It means the disk accelerates faster. So the solid disk will be reach the bottom of the inclined plane first because it has a lower moment of inertia, allowing it to roll faster compared to the ring with the same mass and radius. Number 7, A planet orbits around a star in an elliptical orbit as shown below, based on this diagram. At point A, the planet is closest to the star, and at point B, it is furthest from the star. So there are 2 points, A and B. When point A, it closest to the star, and when at point B, it is furthest from the star. As the planet orbits the star, it has a moment of inertia I equal mr squared, where m is the mass of the planet. State what r represent in this situation. So I have provided my opinion about it. R represents the distance between the center of planet and the star's center at any given point in its orbit. So there are two R. Okay, this is RA, radius when or distance when planet in point A, and this is RB, or the distance when the planet at point B. So based on this diagram, that RA less than RB. So using conservations of angular momentum, that the linear speed of the planet is greater than at is is greater at A than at B. Right. So the angular momentum, or L, we can determine through the formula L equal moment inertia times angular velocity, moment inertia mr squared, while the angular velocity is v over r. So we can simplify r divided by r m r v. We are going to find the linear speed. V is the linear speed, r is the distance, m is the mass of planet. So if V is the subject, this formula becomes L over m times r. This one. V is the linear velocity, right? Based on the diagram that RA less than RB. If RA less than RB, it means VA. The implication is VA will be greater than V linear velocity on point A greater than the linear velocity when the planet on point B. Why? Because the denominator less when R A and R B, if you compare the denominator less uh, when if denominator less, if the it means the implication for the velocity, right? So uh, the lowest of distance or radius implication for the linear velocity. The the smaller the smaller radius, the greater velocity or linear velocity. Next, suggest why in the situation the magnitude of the linear momentum of the planet is not conserved. Linear momentum is not conserved, whereas the magnitude of the angular momentum is conserved, right? I have provided my explanation about this question. Linear momentum, P is not conserved due to the difference of linear speed, right? Linear momentum is the product of m and v, right? Mass times linear velocity. So linear velocity affected by the distance, the radius. Okay, so the radius affect to the linear velocity, and the linear velocity affected to the linear momentum. So therefore, the linear momentum is not conserved. When whereas the angular momentum or L M R V, angular momentum gravity acts towards the center. So the gravitational force act towards the center and therefore does not create a net torque. So there is no uh, affect the gravitational force for the value of angular momentum. So therefore the angular momentum not conserved. A. The pressure P and volume V diagram represent a Carnot cycle for an ideal monoatomic gas. This the diagram. So using the first law of thermodynamics that during the process from A to B, energy is applied to the gas, right? According to the first law of thermodynamics, uh, the equation can express as delta U equal Q minus W. Delta U is change in internal energy of the gas. Q is the heat added to the gas. W is work done by the gas. For an ideal gas undergoing an isothermal process, the change in internal energy, delta U, the change in internal energy is zero. So you can writing that delta U equal zero. Why? Because of the temperature remains constant. So that's why delta U equal zero. Uh, on this diagram, uh, this diagram that V or volume, volume B greater than volume A. If you compare in this V axis, that volume B greater than volume A. If volume B greater than volume A, so the value of natural logarithm or ln VB over VA, the result is a positive number. A positive number, it means greater than zero. So it means ln VB over VA greater than zero. So, or positive number. So, work done result, the implication, the work done result or W, the W, of course, the W result is positive or W, sorry, or W greater than zero. Based on this information that delta U equal Q minus W and delta U equals zero. So Q minus W equals zero or Q equal W. And a relation with this statement that Q equal W greater than zero. The following data are given. This one, so that the volume of the gas at D is about this number, right? So VD, this is VD, this is PD, this is PA, and this one is VA, right? Through adiabatic formula, for the adiabatic formula that PV power gamma equal constant, which gamma value is the adiabatic index 5/3. This for monoatomic ideal gas. So we can expand this formula becomes pressure consists of pressure A and pressure B, so pressure D. So pressure A times volume A power gamma equal PD VD power gamma. If VD the subject, we can rearrange this formula, becomes PA power gamma over PD. Gamma is 5/3, so VD power 5/3 equal VA power 5/3 over PD. So VD equal VA power 5/3 over PD power 3/5. Now substitute all numbers here. PD equal PA, this one, 4.3 times 10 power 5. Then VA, this one, 2.2 times 10 cube power 5/3 over PD. This one, 1.7 times 10 power 5. Of this power 3/5. And the result is, if you calculate, the result 0.003839 rounded to or simplify becomes 40.84. This according to significant figure 10 power minus 3 meters. Calculate the efficiency of this Carnot cycle. Efficiency is 1 minus Td over T A times Tn times at A. So while Td over Ta is 1 minus Pd, pressure, volume. Okay. So 1 minus Pd is 1.7 power 5 times this number 3.84 times 10 power minus 3. over PA 4.3 times 10 power 5, and VA is 2.2. 10 power minus 3. Divide becomes 1. Divided becomes 1. And if you calculate, the result is 1 minus 0.69. And it is 0.31, or in percentage, 31%. 0.31 times 100% equal 31%. Number 9, the thin lens equation model rays passing through the center of a lens as undeflected. Outline why a ray passing through the center of the lens can be assumed to be strike. I have provided my answer, my opinion about this question. One. So students, you may copy my opinion, or you may add something. This is my opinion. Right. I will not reading this. I continue. A ray diagram for a thin diverging lens is shown. This diagram. The question: the lens forms an image of the object. Draw the image and the rays from the object to show the formations of the image. Okay. So the first step, I would like to create a straight line towards lens from the object, rays, and then this ray, and then to F. You may using your ruler for this, and this is the image. Okay. Next, I will continue with the next ray. The next ray from image towards lens, and then from the top of object towards F, okay, through this point. So that's the rays and the image. Estimate the linear magnifications of lens, right? So we need to find the object distance and the image distance. The object distance, that's the object distance. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, and this is the image distance. 1, 2, 3, 4.5, right? 10 and 4.5. And 4.5. And the magnification is image distance over object distance. 4.5 over 10. And this is 0.45. That is the magnification. Next. Explain how spherical aberrations arises for real lenses and how it can be reduced. I provide my opinion, and I will not add something. This enough, I think. This opinion you may copy, okay, or if you may add something, you may add something. All right, students, let's continue. An optical compound microscope in normal adjustment is composed of an objective lens of focal length 0.82 centimeters and an eyepiece lens of focal length 2.9 centimeters. An object is placed 0.91 centimeters from the objective lens. The image is formed at the near point, 25 centimeters from the eye. Show that the angular magnifications of the microscope is about minus 90. Yeah, it's about minus 90. Right. Great. Okay. Firstly, I would like to find how to calculate the distance of image through this formula that 1 over uh, f object is equal 1 over the object or distance object plus 1 over the image distance. And if the image distance, the subject, this formula becomes 1 over f object minus 1 over the object. And it's equal 1 over the image equal 1 over f object is 0.82 minus 1 over 0.91. And if you calculate this fraction, calculation 0.1206, that is 1 over the image. That means image distance equal 8.29 centimeters. That is image distance from the objective lens. All right, so 8.29 centimeters from the objective lens. Now I would like to show uh, the sketch like this I have prepared. This one. Look that this is the positions of the object. So this is the distance of the object, and then where is 8.29? 8.29 is from this one. 8.29. Okay, from this point to here. This is the object, and the image. According to information, that 25 centimeters from the eye. So 25 centimeters. This 25. Wait. 25 centimeters. This is the eye here. Okay. This is the eye. And this the 25 centimeters from 25 centimeters. This is eye lens. This is objective lens. This objective lens, and this is the eye. Yeah, this is the eyepiece lens. This one, eyepiece lens, and this is the objective lens. So from from the eyepiece lens to eyes is 25 centimeters. So the image occur on our eyes. Think clear? Let's continue. The final image through the eyepiece is magnified. State two other characteristics of the final image I have provided also, virtual and inverted. Explain why the refractive index of the cladding in a step index optical fiber is only slightly less than the refractive index of the core. For these questions, I have provided my opinion, my explanation, my briefly explanation. This my explanation. You may copy or you may add with your opinion. I will not reading for this. I think clear. And as well, this one, next questions explain how a graded index fiber reduces the effects of waveguide dispersion. I have provided as well my opinion, this, and I will not reading for it. All right, let's remove. C. An optic fiber has an attenuation per unit length of 1.1 decibel per kilometer. Determine the maximum length. It means we are going to determine L. Determine length of the fiber so that at least 4.0% of the initial power transmitted reaches the end of the fiber. To find L, I'm gonna use the formula, a formula for attenuation of light in optical fibers, and the formula says that P out equal P in multiply 10 power minus alpha L over 10. Okay. L is length of the fiber. What is P out? P out is the power at the end of fiber. P in is the initial power, right? And alpha is the attenuation coefficient, right? Uh, Alpha is for attenuation coefficient is 1.1. This information 1.1 decibel per kilometer. That one, right? Now, I would like to rearrange this equation becomes like this: P out over P in equal 10 power minus alpha L over 10. Why? Because the desired fractions of power at the end of the fiber is 4%. This one. This is the desired fractions of power at the end of the fiber, right? So it means uh, P out over P in is equals 4%, 4.0%, or in decimal, 0.04, like that. So I would like to substitute this number into this equation becomes 0.04 equal 10 power minus 1.1 L over 10. So we're going to find L, right? According to the logarithm rule, we can write it like this, that log 0.04 equal log 10 power minus 1.1 L over 10. Or it's going to be log 0.04 equal minus 1.1 L over 10. Or I would like to write it like this. Wait. Replace the position minus 1.1 L over 10 equal sorry, supposed to be this is log 10 according to logarithm rule. So it becomes 1.1 L because log 1 is log 10 is 1. So 1.1 L over 10 times 1. It is 1 minus 1.1 L over 10. And log 0.04. Okay. And log 0.04 is minus 1.39794. This. So we can substitute this number into this equation. It becomes minus 1.1 L over 10 equal minus 1.39794, like that. We will use this space. So we can arrange this equation becomes minus 1.1 L equal 10 multiply this number becomes minus 13.9794, like that. So it means L equal minus 13.9794 over minus 1.1. And if you calculate, the result is 12.7085, rounded to 13. And the unit is kilometers. Number 12, the diagram shows the extreme positions of a star is 6 months apart as seen from Earth. The black dots are the fixed positions of a distant stars. The horizontal scale is in arc seconds. So you can see this diagram. Show that the distance to a star is about 10 pc, 10 parsec, right? To solve distance by parallax formula, I will start with distance between stars. This star and this star, look the distance 0.18. Right? So parallax angle is half of this number of angular shift. Okay, so we can writing that P parallax angle is 0.18 over 2, right? So it equals 0.09 arc second, right? Now, to solve distance by parallax, we are going to using the formula that the formula says that d or distance equal 1 over p, right? So it means p is this one 0.09. So d equal 1 over 0.09, and the result is 11.11. If you calculate this 1 over 0.09, 11.11 PC. Okay. PC is parsec. Okay. Calculate the ratio distance to star A, distance from Earth to the sun, right? So 1 parsec, I would like to start with 1 parsec. One parsec. 1 parsec is approximately to 3.26 light years. Okay. And then one light year, one light year, one light year is approximately to 9.46 times 10 power 15 meters. Right. We are going uh, to use this number. All right. Distance to star A, one. Distance to star A is 35.86 light years. Okay. So we are going to convert 35.86 light year into meters. So it means we have to multiply by this one light year. 16 meters. Light year. Okay. So the result is, wait, this multiply becomes, wait, yeah, this I have calculated. 339.24 10 power 15. And approximately, it's meters, approximately becomes 3.4 to significant figures, 10 power 17 meters, of course. Right. Now, distance from Earth to the Sun. Distance from distance from Earth to the Sun. It is one astronomical unit. Okay. One astronomical unit is 1.5 times 10 power 11 meters. So the ratio, according to this information, the ratio equals 3.4 10 power 17 meters over 1.5 times 11 meters. It is 2.267 times 10 power 6, 17 minus 11, rounded to 2.3. Okay, next. Star B is part of a constellation. Outline what is meant by a constellation. Okay, I have provided my opinion about this. You may copy or you may add your opinion upon this explanation. Okay. Right, let's continue. The analysis of the stellar spectrum of star B shows that it has a surface temperature of 9,900 Kelvin. Star B is a main sequence star With a luminosity of 25, luminosity of the sun, this the symbol. This is the symbol of luminosity of the sun. Where luminosity of the sun, this is the symbol where this one is L, sun is the symbol of luminosity of the sun. Outline how the temperature of a star can be determined from a stellar spectrum. We can determine temperature by wind displacement law. The wind displacement law, I would like to write in here, wind displacement law. It says that lambda maximum equal B over T. Lambda maximum is the wavelength at which the star emission is strongest. Okay. How about B? B is wind displacement constant, and B, the constant number is 2.898 times 10 power minus 3 meters Kelvin. That's B. And T is the surface temperature of star in Kelvin. So how we determine temperature? So we just rearrange this formula, becomes B over lambda max, or 2.898 times 10 power minus 3 over lambda max. And the temperature is in Kelvin. Next. Predict the likely final stage in the stellar evolutions of star B. Right. The final stage in the uh, evolutions of star B depends on the star B mass and luminosity. Based on depends on mass and its luminosity. The relations of luminosity and mass we can determine. I'm gonna using this space. Okay. We can use this rule that luminosity proportion to m cube, I mean. So it means we can say that m equal L power 1/3, right? So according to information that L equal 25, 25, L equal 25. So I'm gonna show you this one, 25 luminosity of the sun. So if you calculate this number, m equal 2.9. Okay, this is okay mass of the sun. So m equal 2.9 mass of the sun. That one. Next, I have explanations about these questions related with this calculation, this result. This is my explanation. Okay. You may add something or you may copy my explanations about this part. So this is the conclusion, the summary, this one. All right, let's continue. Another star in the constellation is separate variable outline the reason for the variations in brightness of these stars. I have opinion also. I have provided my explanations about this question. This is my explanation. And the last one is my summary. So this is the first one, the second one, the third one, and the last one is my summary. Right. Okay, I think clear. 13. The cosmic microwave background CMB radiations is observed to be largely isotropic with a temperature of about 2.76 Kelvin. Explain how these features of the CMB provide evidence for a hot Big Bang model. I have provided my explanation about this question, this, and you may add your opinion or you may copy this opinion. All right, let's continue. A galaxy is observed to have a redshift of 0.01. Hubble constant can be assumed to be 70 kilometer per second MPC. Calculate in MPC the distance to the galaxy. To calculate the distance to the galaxy, we can use Hubble's law, and the Hubble's law says that velocity of a galaxy equal Hubble constant multiply distance. Okay, if we are going to calculate distance to the galaxy, d, it means d the subject, this formula being v over h0. And now we are going to find phi first because h0 is this one, Hubble's constant 70 kilometer per second MPC. And velocity, the formula is z times c. Z is redshift and c is speed light. So it becomes 0.01 times speed light is 3 times 10 power 5 kilometer per second. And it is 3,000 kilometer per second. So distance equal 3,000 kilometer per second over this one 70 kilometer per second MPC per MPC. Right, becomes 1, and if 3,000 over 70, that is 42.86 MPC, or for rounded to 43 MPC. Determine the age of the universe in seconds, corresponding to the above value of Hubble's constant. Give your answer to at least two significant figures. We're going to using the formula that T0 equal 1 over H0. But we have to convert first H0 into second, right? Here, H0 is 70 kilometers over S MPC, like that. So it becomes 70 kilometers, and then second, 1 MPC is equal to 3.09 times 10 power 19 kilometers. So this is 3.09 times 10 power 19 kilometers. And then 70 divided by this number, that is 22.654 times 10 power minus 19 per second. Or in significant figures, 2.26 times 10 power minus 18 per second. Next, substitute into this formula, T0 equal 1 over 2.26 10 power minus 18. And if we calculate, the result is 0.4425 10 power 18 second, rounded to 4.42 times 10 power 17 second. Explain how the observation of type 1a supernova provides evidence for an accelerated expansion of the universe. I have provided my explanation as well. This one, you may copy or you may add something into this opinion, into this explanation.